Hello everyone, we will continue with refining. We have 3 steps in oil processing. Refining is the major step. And the first step is preparing the raw material for oil processing. Then, in the next step, oil is separated from its source. And this step is called extraction. We will see 2 major oil extraction processes: expeller pressing and solvent extraction. And the last step is refining. We can simply define refining as the processes used to make crude oil suitable for human consumption and some food applications such as cooking or frying. So we obtain crude oil from extraction process. Then we process this crude oil with refining. So it will be suitable for our consumption. It will be edible. We start with removing foreign materials. Because when we harvest the oil seeds from fields, there are some foreign materials in it, such as wheat, seeds, stones, metal, etc. First, we need to separate those foreign materials because they can damage processing equipments and also they will affect the composition of the oil extracted. Therefore, they must be removed. Here you see a sieving machine used to separate foreign materials from oil seeds. Sieves and screens are used to separate foreign materials by size and shape. Air fans are used to separate materials by density. Light materials are blown away by forced air. Also, in some systems, magnets are used to separate metals. When the raw material is free of foreign materials, the next step is extraction. So this is the step where oil is separated from its source, such as separating oil from olives, soybeans, or sunflower seeds. So we will have most of our discussion on oilseeds as they are the major oil sources in food industry. But I want to show how to isolate animal fats too. Isolating animal fats. It's actually an extraction process, but for animal fats it's called rendering process. Lard and tallow are 2 main animal fats. In rendering process, fat portions are trimmed, separated from meat, finally chopped and heated with water. I will show you in a different page. So we have fat portions in water. And it will be heated. So when heated, the fat will melt and be liquid. So we will have an oil and water mixture. What happens when water and oil are mixed? They will separate from each other. The oil will float on top. Because fats and oils have lower density than water. Then it will be separated from water using a centrifuge. Some animal fats may be refined, but refining process is most widely used for plant oils. So this lecture will focus on plant oil processing. So let's see plant oil extraction methods. Expeller pressing. Expeller pressing is the most basic extraction process because no solvent is needed. Simply, oil is squeezed out of the oil seeds using an expeller like that. It's a clean process because no toxic organic solvent is used. But the disadvantage is that the oil yield is low. With this method, we cannot extract all of the oil. Good amount of oil stays in the cake, oil cake. You can obtain clean oils. Heat is also low. The temperature of the process is around 40 degrees. So it's not very high. So it's an advantage. It's a gentle process. Low temperature helps preserve the oil's natural characteristics. Just friction and compression of the seeds should be controlled to prevent excess heat generation. Again, as we said, the major limitation is the low oil yield. Other extraction method is solvent extraction. It's the most common method. In this process, a solvent is used to extract oil. It's based on solubility. First, you need to identify a good solvent for your solid, which is oil. Please remember like dissolves like rule. Means that if you have a polar compound, you need a polar solvent. For oils, the most common solvent used in industry is hexane. It's an organic solvent. It has relatively low cost and low evaporation point. So during solvent extraction, oil seeds are first crushed to increase the surface area. So when you have high surface area, you will have more contact surface between your seeds and hexane. Therefore, you will have a more efficient extraction. Then the flakes are soaked in hexane and mixed. At the end, we obtain hexane plus oil mixture, which is called micella. Here. It is hexane plus oil mixture. We call it micella. Now we need to remove hexane. Then micella is heated above the boiling point of the hexane to separate the oil. The evaporation point of hexane is around 69 degrees Celsius in this range. But oil has much higher evaporation points, above 200 degrees Celsius. Therefore, hexane will evaporate and you will have just oil. And this oil you obtain at the end is called crude oil. And this oil will go to the refining process. Let's see the advantages and disadvantages of the solvent extraction. It's more efficient than mechanical extraction, which is expeller pressing. Over 99% of oil can be extracted with this method. Remember, in the expeller pressing, the major limitation is low oil yield. Most of the oil stays in the oil cakes. Here, with this method, the remaining oil in the oil cakes can also be extracted. I will just write expeller pressing here, so it's the same thing. So let's see what are the limitations. Solvents like hexane are not food grade. They are toxic and flammable. Oils extracted with solvents do not comply with natural or clean label claims. In the previous slide, we said we heat the micella and remove the hexane by evaporation. However, it's still possible to have some ppm levels hexane in the oil. Maybe very low ppm level. But still, it's a concern if that residue remains in finished oil. It's potentially dangerous. That's the limitation. Okay, we learned about two main extraction methods and we obtain crude oil from these extractions. Now the next step is refining. So the question is, why do oils need to be refined? Impurities and contamination can introduce negative quality, safety and stability traits into the oil. So in this table, you see impurities or contamination from soil in the first column and also the undesired impact on oil in the second column. Actually, many of these impurities are not harmful, but they cause problems during food applications such as frying or cooking or storage. For example, we have phospholipids in crude oil. And they are pro-oxidants. Which means they will oxidize and reduce oxidative stability of the oil. That's why they must be removed. Another example can be pigments. They are not harmful, but pigments will burn during frying and cause some color problems, color change in the oil. That's why they must be removed. Another impurities are free fatty acids. They will cause an acidic taste and they will cause oxidation as well. Therefore, they must be removed too. On the other hand, we have harmful impurities such as pesticides, aflatoxin, polycyclic aromatic hydrocarbons. They have potential health effects, even they can be carcinogenic to humans. That's why they must be removed. So when we remove most of these impurities, the remaining oil will be almost 100% triglycerides. So these impurities must be removed to produce oil with desired color, flavor, and shelf life. Let's see the refining processes. Oil refining processes are not the same for all oils. Here you see an example for cottonseed oil refining. It depends your starting material, your starting oilseed, and the end use. For example, extra virgin olive oil. It's not refined, it's just pressed, and that's why it's not suitable for frying. You shouldn't cook with extra virgin olive oil. It's not stable to heat and degrade quickly. It's more suitable to use in salads. Let's see the refining processes. The first one is degumming. Here we remove the gummy materials, which are phospholipids. Because phospholipids will cause the formation of water in oil emulsion. And these emulsions will make the oil cloudy. And the water in oil emulsion can present a hazard when heated. Heated especially above boiling point of water, which is 100 degrees. It can cause spattering and foaming. Another reason we want to remove phospholipid is that because they contain amines, amine groups. And that amines can interact with carbonyls. And which cause browning products, which is undesirable during thermal processing or storage. So how can we perform degumming? It can be performed by acid degumming or water degumming. Generally by addition of water and acids at around 60 to 80 degrees Celsius. Small amounts of acid are often added to the water to increase the phospholipid solubility. Then aggregation occurs and they can be separated by centrifugation. With oils such as soybean oil, the phospholipids are recovered and sold as lecithin, which is a valuable byproduct. Next step is neutralization. Free fatty acids are removed in neutralization from crude oils because they can cause off flavors, decrease smoke point, accelerate lipid oxidation, and cause foaming. Smoke point. We said presence of free fatty acids decrease smoke point of the oil. The smoke point is also known as burning point. Burning point of oil or fat. It's the temperature at which it begins to produce a continuous bluish smoke that becomes clearly visible. So if we remove free fatty acids, we decrease the smoke point of the oil. So how can we perform neutralization? It's performed by reacting the oil with a solution of caustic soda, which is sodium hydroxide. It's a base. And then removing the water containing the salts of the free fatty acids. Remember, when we react acid and base, we form soap, right? And also water. So this resulting soap can be used as an animal feed or to produce surfactants and detergents. So it's the byproduct of neutralization step. So as the name says, it's neutralization. We have an acidic medium, we have free fatty acids, so we need a base to neutralize it. Then we remove the free fatty acids as soap. The next step is bleaching. As the name says, it's bleaching, it's lightening the color of oil. Because crude oils contain some pigments like carotenoids and chlorophylls. They might produce undesirable colors. So during bleaching, the main impurity removed is color pigments. But we still have some soap, gum precipitation, and maybe some metals from the previous refining step. Maybe very little, again ppm level. They can also be removed during bleaching step, but that's the main impurity we remove in bleaching, the pigments. That's why it's called bleaching. See the difference between unbleached and bleached oil? There's a dramatic difference between these two oils. So these color pigments are removed by mixing the hot oil with absorbents such as bleaching earth, or we also can call bleaching clay. They act like a sponge. Absorb all the color pigments. So after the process is done, this bleaching clay or bleaching earth is removed by filtration. This process is usually done under vacuum. So why are we using vacuum? So vacuuming means we remove air, so there won't be any oxygen, no oxygen, and there won't be any oxidation. The reason we don't want any oxygen in the environment is that this bleaching clay can act as a catalyst for oxidation reaction. So it might increase the rate of oxidation. That's why this process is usually performed under vacuum with no oxygen in the environment. Okay, next step. Let's see the next step. It's winterizing or dewaxing step. We call it dewaxing because waxes are removed during that process. Actually, waxes are not harmful, but consumers do not want that cloudy appearance, and during cooking they might burn. That's why we want to remove waxes from oil. But some oils do not contain waxes. So this step can be skipped for some oils. So how waxes are removed? First, the oil is heated to ensure the oil is fully liquid, because there could be some oil crystals in it. That's why first we heat it. Then the oil is typically chilled. Generally chilled to less than 10 degrees Celsius for a certain amount of time to crystallize high melting waxes in the oil. Then we can use a filter aid and filter that waxes from your oil. Again, some oils like sunflower, corn, cottonseed and flaxseed oil, they don't need dewaxing process. Let's see the next step. Deodorization. It's typically the final step before the oil is packaged. Crude oils contain undesirable aroma compounds, volatile odors, Again, there will be some remaining free fatty acids remaining from the other step, the residual free fatty acids. Also, there are some harmful compounds like peroxide, polycyclic aromatic hydrocarbons, and pesticides. They are toxic and carcinogenic, so they can also be removed with deodorization step. But volatile odors are the main impurity removed during deodorization. So how are they removed? They are removed by subjecting the oil to steam distillation at high temperatures and low pressures. You just basically pump very hot steam into your oil. And all volatile odors will be gone after that process. The free fatty acids will be removed also, because their evaporation temperature is lower than triglycerides, because we want to keep the triglycerides and remove free fatty acids. But this deodorization step might have some side effects, because this process requires very high temperatures. Let's see the side effects of deodorization. Here, high temperature is good to increase the yield, but it also increases the formation of, for example, trans fatty acids, which is bad for health, and cause formation of some oxidation byproducts such as conjugated dienes, which is undesirable. That's why there's the suggested upper temperature limits and time for that process to prevent the formation of that undesirable byproducts. It's generally 240 degrees Celsius for 2 hours or 270 degrees Celsius for 30 minutes. Because we can also lose some valuable oil components like carotenoids, sterols, and tocopherols because of that high temperature. Let's see how refined oils should be. Refined oils should have minimal odor, bland taste, transparent appearance with minimal color. Here, the first one is unrefined oil, and see the color change with each refining step. The color gets lighter with each step. And refined oil will have increased shelf life stability. And these are the specifications for a refined oil. Still, there could be some impurities like free fatty acids and peroxide value, some metals at ppm level. Yeah, but they should be in an acceptable range. And it should be composed of like almost 100% triglycerides. Chemically, they are called triglycerides. That's all for refining step. Let's see the physical properties of oils and fats. Molecular structure and composition affects melting properties and sensory properties of the oils, such as texture, appearance, and flavor. So why these physical properties of oils and fats are important? Because spreadability is important for spreads. They should be spreadable when we get out of refrigerator. And it should stand up, not collapse to a puddle of oil. The physical properties are important for chocolate, because chocolate has cocoa butter. And physical properties of cocoa butter affects the texture and taste of the chocolate. A good chocolate should be solid at room temperature, and it should melt in the mouth with a cooling sensation. And it should have a glossy surface for a desirable look. The incorporation of air, plasticity, and consistency and solid-liquid ratio are important characteristics for shortenings. Rheological properties. So rheological data help us to understand the fluids. It's defined as the science of deformation and flow of matter. It deals with how materials respond to applied stress. It defines the relationship between applied stress and resultant deformation or resultant flow. Rheological properties of oils and fats are important to have an idea about product pourability, mouthfeel, processability, like mixing, spraying, pumping, heating, cooling. Here, shear stress is the force acting on unit area required to cause flow. A shear stress can be like mixing of oil or fat, pouring, and shear rate indicates how fast an oil or fat flows when this shear stress is applied. And this graph is called flow curve. So plotting shear stress versus shear rate gives us flow rate. Based on this relationship between shear stress and shear rate, fluids fall into two main classifications, Newtonian or non-Newtonian fluids. So liquid oil shows Newtonian fluid behavior. Viscosity is constant with increasing shear rate. On the other hand, fats show non-Newtonian behavior, specifically Bingham plastic. So that means fats need a yield stress for flowing. So this is the yield stress. It's called yield stress. That means you are applying a stress to a fat, for example, butter. Here it's solid. Here solid again. And it reaches the yield stress. So when the stress above the yield stress value, then they exhibit free flowing, like a liquid nature. So here it acts like a liquid above yield stress value. Okay? Just visualize, you have a butter, you are mixing it or blending. First it acts like a solid fat. Then it reaches a certain stress value, which is called yield stress. Then it starts flowing. So there is no flow until it reaches the yield stress value. Then after yield stress value, it acts more like a liquid. But oils are Newtonian and they are just flowing with mixing, pouring, pumping. Oil viscosity is constant with increasing shear rate, but as a general rule, viscosity of oils decreases with increasing temperature. So rheological properties of oils and fats are important to understand the pourability, mouthfeel, and also how they will behave during pumping, spraying, transporting, or when they are stored, when they are heated or cooled. So another important physical property is density. You know, density is mass over volume. Density information of fats and oils are important for designing food processing operations, such as pumping oils and fats through a pipe. So we need density information for that. Generally, oils have lower densities, as you see here, compared to fats. But both oils and fat densities decreases with increasing temperature. Density depends on the packing of the triacylglycerols within the oil molecules. The more efficient the packing, the higher the density. Triacylglycerols with saturated fatty acids pack tightly, therefore they have higher density. So we will learn about packing later in crystallinity section. Let's look at the thermal properties. The most important thermal property is melting point. It's the temperature at which solid becomes liquid. Actually, we don't use the term melting point, we rather use the term melting profile. We will learn about it later in detail. Melting profile for oils and fats. Because lipids melt over a temperature range, therefore we actually use that melting profile instead of melting point. Again, we will see it in more detail later. But now I can simply explain, because fats are mixtures of different triglycerides and each triglyceride has a different melting point. When we heat a fat, some triglycerides start melting because they have lower melting point, but some do not melt as they have higher melting point. That's why we are talking about melting profile instead of melting point. So other thermal property is specific heat capacity. It's 2 joule per gram for most lipids. It's a high heat capacity, that means oils and fats hold a lot of heat before they begin to get hot. So they store good amount of heat. Enthalpy of fusion is the other thermal property. It's the energy absorbed released during phase transitions such as melting and crystallization. Thermal conductivity is an important thermal property. Fats and oils are poor conductors of heat, especially compared to water. That means we spend more energy to heat oils and fats. Optical and electrical properties are worth mentioning. Refractive index is a property we use to have an idea about the degree of saturation. How much saturated or unsaturated fatty acids are there. So refractive index value of fats and oils falls between 1.43 and 1.45 at room temperature. And it increases with increasing chain length, increasing double bond number, increasing conjugation of double bonds. Because when there is more double bonds, those double bonds refract light more. As a result, the refractive index will be higher. Okay. Bonds refract light more. UV absorption property is important. Pure triglycerides have little color compared to commercial oils. And you know the color of the oil will affect the UV absorption. In emulsified foods, lipids contribute to opacity. So we use information on UV absorption for HPLC analysis of different lipid groups. And lipids tend to have fairly low relative dielectric constants because of the low polarity of the triacylglycerol molecules. So that's all for this lecture. Please let me know if you have any questions.